Good morning, good afternoon, good evening. A lot of people have joined already, and a lot of have already registered for the seventh session by EBIPSA Education webinar series. I'm very glad that people are receiving this very well. And today we have eminent person with us to talk about daylight performance prediction. And I'm sure that all of you know who Christopher Reinhart is. So Christopher is a Christoph is a building scientist and an architectural educator working in the field of sustainable building design and environmental modeling at MIT. Christoph heads Sustainable Design Lab, an interdisciplinary group with a grounding in architecture that develops design workflows, planning tools, and metrics to evaluate environmental performance of buildings and neighborhood. He's going to talk about a chapter which he has authored in a book on daylight performance prediction. We will start, and over a period of time, you can shoot questions to me on the question pane. And if you cannot hear us properly, just send me a message. But before sending message, you can check your connection. Sometimes it happens that your jack is not properly connected. You might not be able to hear. But you can send me a message over chat pane. We'll start over to Christoph. Christoph, thank you very much for offering this webinar. We are very glad that you could spend some time on this. And welcome to EBIPSA webinar series. Over to you.
Thanks a lot, Rajan, and thank you all for joining here this morning. I think it's really fantastic that EBIPSA is spreading the word about the book and about our activities by this webinar series. And yeah, thanks again to Rajan for setting it up, for reminding me diligently that I should be here. And thanks a lot for Jan Hansen and Roberto Lombard, who first took the leadership initiative years ago to put this book together, and again now for making us updating it. This gave me a good opportunity to revise the field of daylight performance predictions. So what I'm going to present today is an overview of computer-based daylight simulations for buildings and for urban design. And as so many things that we all do as academics, this is really what I'm presenting today is the product of lots and lots of discussions, both over the last decades with various members of this community and of our lab at MIT, as well as a more intense debate yesterday, what we should put in, how we can try to summarize in an unbiased way the whole field of daylighting. So hopefully this is going to be useful to you. And just to in case you want to learn more, to give you an overview, as Rajan said, what I'm presenting today is partially based on this building performance simulation for design and operation book from EBIPSA, and we will have a new edition coming up at one point. But also, if you're interested more in the background of daylighting and the theory behind it, there's a book called Daylighting Handbook, which I am drawing from. And finally, to get into even more details on daylight simulations, we are in the last phases of reviewing a new handbook, which is dedicated to the topic, and reviewers are in, so I hope in the spring to have this volume out. Of course, for all slides that I'm presenting, I try to provide the primary reference as well. So starting off, this is an outline of my talk, and I wanted to break this whole all this up into 4 subsections. The first one being related to the motivation. So why daylighting? Why are we interested in that? Why do we want to simulate light in and around buildings? And after that, I provide an overview how to simulate daylight, looking at literally the last 100 years. How have people come up with methods to predict daylight in buildings? And where are we today? And after we know how to simulate, we are actually going to look at the computer to help us what we should actually simulate. So what kind of metrics are in place, what are new metrics that are on the horizon. And finally, I try to, at the very end, talk about some new emerging topic and where I see the field going right now. So daylighting, while is that, of course, there are whole classes and books dedicated to the topic. What is daylighting? It's the act of lighting the interior and or the exterior of a building with natural daylight. And I think a key motivator is just visible in the image that you see on the screen here in the Cambridge Public Library. If this weren't a curtain wall with a window and daylight coming in, if this would just be a regular opaque wall, we would find it all very odd that people are looking there. But the moment we have a window, we find it natural that everybody is drawn towards the light for its various benefits, especially the daylight. Apart from the obvious that it's aesthetically pleasing, it's of course visually stimulating to see the light go by as you're looking out of a window. The view, the full spectrum color rendering, the changing of the colors over time, this is all that we know more and more is helpful and productive for people in buildings. And then the other big topic when it comes to daylighting are, of course, related to resource efficiency, energy savings, and peak load reductions. And pretty interesting when you look at that image here. In this case, the first couple of points are very well addressed, but the lighting is on when this image was taken. So I think it's very important to realize that there are these conflicting goals when it comes to daylighting. We have to somehow try to hit on all, depending on what our main motivation is as designers. So in order to tackle these diverse aspects of daylighting, Jan Wienold and I worked a couple of years ago on this framework for daylighting. And we start off with the observation that in order for any space to be called daylit, you obviously have to evaluate the daylight availability. So is there any light within the space? And then the next part is, of course, that daylight needs witnesses. So we want to see how light has an impact on people within a space. Is it the right amount of light, or is it too little? Then we have to turn on the electric lighting. Is it too much? Then we might be experiencing glare automatically or with manual control. So there's this very interesting and complex feedback loop going on, which then, of course, if we close the blinds, has an impact on the daylight itself. And all of this, if we understand that right, feeds them into the actual heat balance and then energy use of a building. And I'm not going to talk about occupant behavior. This is what Adesha talked about a couple of weeks ago, or about thermal energy analysis. That's in chapter 5, and Jeff Spittler talked about that a while ago as well. So I'm concentrating really on daylight availability and visual comfort here. So when we now say, well, let's use the computer to help us design for daylighting, it's of course interesting to first take a step back and understand, well, what are people actually doing right now and how are they implementing daylight into buildings? And these are results from a survey that we did a while ago, 10 years ago, and we distinguished answers from designers and from engineers. Not surprisingly, we've all been in daylit spaces, so a key ingredient in daylighting design is experience from previous work, from just our previous experiences in our life. And then there's this interesting relationship that early on in the design process, we tend to, due to time constraints, historically more concentrate on rules of thumb, which are validated or made up, and then later we are actually turning towards daylight simulations themselves. So I think it's very important when you are concerned with this field that you always understand this context around these tools are being used. And it's important that there's a consistency, for example, that the rules of thumb work well with the computer simulations and so forth, in the terms that they have not conflicting but aligned messages. And that gets us now to daylight simulation. So what is a daylight simulation? It's the computer-based attempt to model the luminous environment around you. And effectively, what we are trying to mimic are two types of measurements. The one that you see on the left-hand side and the one that you see on the right-hand side. And these are, it's important to understand what the difference here is. Both are, in quotations, pretty false color images that you see. But if you are modeling the luminous distribution of a space, you have something that looks somewhat like a rendering of a space, and we get more into that a little later. Only that what it is, it's as if somebody was taking a luminance meter and was measuring pixel by pixel the amount of visible light coming from a certain direction. And when you put all these pixels together, you have an image that gives you a better sense of how, from an observer's perspective, a space actually feels. So this is viewpoint dependent. On the right-hand side, what we've been using more historically are illuminance sensors and an illuminance grid. So we take a sensor that measures the amount of light that falls on a surface. And if we are putting the sensor on a fine grid, then we can create what you see at the bottom right, this illuminance distribution. So how much light you have where within a space. And of course, the clear attraction of the illuminance distribution is that when you design a building and you're used to at least partially look at your building as a floor plan, then when you look at your building and plan, you can overlay this information. And as a designer, that's of course very useful to link where daylight is to your windows and your overall programmatic use within a space. So now we're moving on to, after having motivated somewhat why one would want to simulate daylight, of how this is actually being done. And these are the key ingredients that one needs to do a daylight simulation. So you see a scene, a 3D geometry of a space. You need the material descriptions of all the surfaces within your screen. You then need a sky model above, that's your light source, and you combine all of this into a global illumination algorithm. And that pops them out, the luminance distribution and the illuminance distribution that we just talked about. And very important, you also then need a metric or a design question. So we are not doing simulations for simulation's sake, but there has to be a clear goal. And the earlier you are aware of what this is going to be, the more effective your simulation is going to be, your analysis. So let's go through all of these different components one by one, scene geometry, where this is coming from. Well, if you're in today's architectural design, you are used to modeling in CAD and in 3 dimensions. And here I just provide a little case study of a project that happened in Cambridge by Renzo Piano Building Workshop, the Harvard Art Museum extension. And here on the top left, you see a photo of the finished space. And on the top right, you see a sketch that was made during the design process that gives you an idea of how a designer, you might want to try to get a sense of the light and how a space is going to feel. And then at the bottom left, you see the typical architectural rendering as is being created in architectural practice or for in schools of architecture as well. And what this does, it of course has light as a component, but the accuracy of the lighting simulation is not per se the main goal here. Here you could say, I want to again get a sense of the space, I want to see how the structure is going to feel, and it has a certain purpose that way. Now, based on the same Rhino model on the bottom right-hand side, you see the actual luminance distribution. So this is a radiance-based daylight simulation. And here suddenly, it's all about, it's really a 2D set of measurements that tells you, well, under certain conditions, how much light am I actually going to get within that space? And the way I just described it, since architects are working during design on this 3D models anyhow, this is where your CAD model for the daylight simulation can come from as well. So that's our first component. If we're now moving on, how do we model surfaces within our scene? And there are some very simple models. We could just use purely diffusing reflective surfaces. But just to give you a sense here, there's a picture of the MIT chapel by Eero Saarinen, where light is reflected off the outside ground and then sneaks into the building from below and creates this wonderful patterns on the wall. This obviously requires that we are more careful in how we actually measure the various surface properties that we are dealing with here. And here you see a snapshot of how one can actually go about that. If you don't have access to any measurement devices, then you can either go to the International Glazing Database, which you can access to the optics window tool from Lawrence Berkeley National Laboratory. And for reflective surfaces, opaque surfaces, you can use this wonderful website, lightingmaterials.com by Olsen Jakubiak, which you see on the top left side, where you have a large variety of measurements that were already done, and you just click on any material that you're interested in, and you get a radiance material that you can copy into your scene. And you get the physical properties with the radiance material, so if you're using other simulation tools, you're able to build a material model out of this as well. But then when you go into existing buildings and you really want to understand some of the properties of surfaces around you, then if you have an illuminance meter, you can do what's shown here on the top right. So you take, for glazing, for example, as a first order of magnitude in illuminance meter with and without the glazing in place under opaque sky conditions. That gives you the visual light transmittance of the material. Or there's this incredibly useful and effective tool, the SIPSI reflectance chart that you can order from SIPSI in the UK, which helps you to, just without any other tools, to estimate the reflective properties, diffuse reflective properties of surfaces in buildings. And if you want to go very fancy, or if you have very complex materials, light redirecting systems and so forth, then typically you will have to try to get bidirectional transmittance distribution functions for these materials. This is the most general way of how to describe material properties. For that, you have to consult probably services, talk with manufacturers, and it becomes a more involved process, but we are certainly able to model these materials as well. So now we're moving on, sky models. What do we do there? This is how we describe the light source, daylight, that we are then going to model. And until the 1960s, our sky model was the uniform sky, top left side, very simple, uniform luminance distribution from all directions coming up. If you go to the bottom left, the CIA overcast sky was an improvement over that. Basically, that's a very continuously overcast sky, which has a brighter zenith luminance than towards the horizon. Very important is rotationally invariant. So any way you rotate your building, you will get the same results using this analysis. And then once people realized when you're in a sunny climate, just using the CIE overcast sky makes less sense. So we first had a clear dedicated CIE clear sky model. And then over time, as we became more ambitious and wanted to really model lighting over the course of a whole year, we would use information from a typical meteorological climate file. This is a chapter in the ADIPSA book 3 where you, that provides information about these files. And then you can effectively model with a general sky model, such as the Paris sky model, any sky condition. So now, since this is of particular relevance for the first daylight simulation methods that were being introduced, is the daylight factor. So the daylight factor is based on the CIE overcast sky that I just mentioned. And the goal at the beginning, when people came up with their first daylight calculation methods, the goal was to model under this particular sky the ratio of inside lighting conditions to outside unshaded lighting conditions. And this is called the daylight factor. So linked to that, the first simulation tools wanted to calculate the daylight factor. So in order to do so, the model being used was what you see here on the screen, effectively saying, when I have a point in the building, there are three main components that I want to calculate. How much direct sky do I see? How much sky do I get light that's reflected off buildings outside or objects before they enter my point? And then internally reflected light. And really, 1923, first type of simple to use daylight simulation methods for the direct sky and for the externally reflected component were these Waldron diagrams by Percy Waldron, which you see one example here on the screen. So the way this works is you had to have these sheets that you see here. And if you were interested in the lighting at any particular point in the building, you would have to basically draw windows. That's what you see here in white, external objects in dark gray, and give the room itself onto this projection. And once you've done that, you have to start counting these squares. So the squares are made that there are 1,000 squares in total. If you have 1,000 squares, then you see the whole quarter hemisphere, and then you would get the maximum value for the sky component. In this particular example, if you were to count all these squares that are white, you end up with 86 squares. If you multiply that through with frame factor and visual transmittance of the glazing, you get a direct component of about 4.7%. So that process, you didn't need a computer, was somewhat bothersome. If you do this now for a site-lit space and you vary the distance to the facade, then effectively you get something what you see here on the screen. So very close to the window, you see a lot of sky, and if I'm moving further and further away, that component becomes smaller and smaller. So the next big innovation was really in 1954, where from the Building Research Station, as the BRE was called in the UK at the time, and Ralph Hopkinson, Jimmy Longmore, and Peter Pepperbridge developed this BRS protractors. And how that worked was that you used an existing section and plan of your building and overlaid this protractors. You could read off certain values and derive the sky components and the externally reflected component from them. And that, of course, had the big advantage that you could relatively quickly get towards distributions within spaces. And then the genius, in my opinion, really came when Andrew Marsh developed with Ecotect in the I guess early 2000s, the first real computational design tool. Meaning that if we want very quick feedback and design with these type of methods, we have to speed them up. And he effectively converted the BRS protractor methods into a simple ray tracing approach, where instead of having to do all of these things by hand, you just shoot rays out in all directions and do the calculations that way. And that was very impressive. If we are now looking at today's state-of-the-art methods and these old approaches to modeling the daylight factor, you get something like this. So similar as I showed before, these are daylight factor distributions predicted on the center axis of a site-lit space with varying distance to the facade. And what you actually see is that in the main area where it really matters, between 2% and 5%, the different methods are pretty much in agreement with each other. There are some slight variations which have to do with how these methods can take in three-dimensional effects of frames or thickness of walls, but overall you're in the right ballpark, which is not surprising because these methods really were mostly developed to model this type of situations. Whereas AGI-32, a radiosity-based method, and Radiance, a ray tracer, came in later to also tackle more general situations. So having said that these methods agree pretty well in simple situations, now, when we actually move on to something more complicated, you see that it's actually worthwhile to use a more advanced tool. So on the left-hand side, you see a simulation based on BRS digital, I call it here. So how much light do you get within the space based on the method that I just showed. And on the right-hand side, you see how Radiance, a ray tracer, would predict how much light there is. And you see significant differences here. So the daylit area changes from 28% to 46%. And in this case, the daylit area is defined as the points within the space where the daylight factor is over 2%. So why is the difference here so pronounced? It's really because the space that we looked at here has very thick walls, and you will have multiple reflections happening for a lot of the light entering the space. And this is something that by definition the VRS method cannot do. So paying attention to your engine and making sure that your engine is validated is incredibly important. So now I'm moving on to a particular simulation program that has been used a lot, the Radiance Light Backward Ray Tracer. It's not the only method, of course, and I talk about some of the other validation studies that have happened for other methods as well in a bit. But I think it's important for you to just have a mental image of how these tools work. So we are following light backwards due to efficiency reasons. We are doing that starting with a camera viewpoint and with an image plane. So the image plane is really how we want to see the world. We are positioning theoretically our eye at the camera position. We have this image plane. And now in order to understand how a scene is going to look, we are shooting rays from our camera position through each of the pixels in the image screen. And then we are hitting various surfaces. And the big advantages of ray tracers is that you can become very detailed in in your material modifiers. So how are the ray tracers going to interact with various surfaces within a scene? And if I now go forward here, you see what the camera would actually see. So we have light being refracted and through the glass sphere. There is refracted, there is reflected light of the specular metal sphere, and then there is more diffuse reflectance happening for the orange sphere. So this is how the backward ray tracer works. And if instead of so this is a luminance distribution, a luminance calculation. If instead of the luminance calculation, we want to use a ray tracer to do an illuminance calculation, then the approach is pretty similar. In this case, we have a sensor here within our scene, but instead of having an image plane, we are shooting rays out in all directions from the sensor. We're spawning them. And then you see here what can happen. You can hit a light source directly, the sun, then you're done. You can hit the sky, then you're done. You can hit diffusing surfaces, and then you recursively spawn more rays, and you keep on going until your simulation discards a ray because the weight of the ray isn't large enough. And that just really gets me to the point, which I'm not going to cover in this presentation due to time constraints, but I want to point out that it's very important. You have to really tell your ray tracer what the complexity and type of scene that you're dealing with is, and how long a simulation should run, how many reflectances should be taken into account, and so forth. And there's certainly material that helps you to do so, but you have to understand really the workings of the ray tracer to a degree to get reliable simulation results. How reliable is reliable? There has been a rich tradition in doing, in validating various ray tracing-based simulation programs and others. Starting with 1995, John Madagievich, until very recently, Andy McNeil and Eleanor Lee. And these validation studies typically involved a full-scale test room taking measurements, illuminance measurements really, in spaces under multiple sky conditions, and then trying the computer using radiance to reproduce these illuminances. Now in 2009, we also expanded this to work with another ray tracer, Mental Ray, which is in Autodesk 3D Max design tool. So the main information to retain from this illuminance validation study is that if we do, in quotation, everything right, then we can typically predict illuminance levels, time series of them, in buildings with a mean relative error of about 20%. Moving on to, this is actually a very recent validation, which was looking at, we now know that radiance can model illuminance distributions, but what about luminance distributions? That is per se, there's no reason why radiance shouldn't be able to do this, but of course it's more complex because you have to understand a lot of details about a space in more detail. If I'm modeling the illuminance at a certain point, then I might get certain surfaces too high or too low, and then the results average out, so I get better results. If you want to do a luminance distribution calculation, the simulation are less forgiving. So what you see here is work just published by Nathaniel Jones from our lab, where we looked at using so-called high dynamic range photography measurements, luminance distributions in a space at MIT, and then using various simulation methods and using both ray tracing from Radiance as well as a new tool which is called Accelerate to reproduce this luminance distribution. And what we mainly found, so just Accelerate is a publicly available tool that uses similar algorithms to Radiance but works on a graphics card, allowing us therefore to a degree parallelize the ray trace calculation and speed it up quite significantly. So the main result of the study that if we want to use these images to understand visual comfort in buildings, especially glare, then these methods yield very reliable results to simulations, as do the high dynamic range photographs. So after this, we are now in a situation where we can model the luminous environment in spaces, in principle, anywhere in the world. So this takes us now to the exciting question of, well, what should we actually simulate in the first place? And starting off, thinking of our earlier framework, looking at daylight availability. So how much light do we have in buildings? And from the perspective of a designer, really what we want to know is not so much under a particular sky condition at a particular point how much light there is, but overall, how much light do I have where, and which part of my building should be daylit and which one should not be daylit. So the main goal here is to have a floor plan and say daylit area, non-daylit area. That's what these metrics that we're going to discuss in the following are doing. So the first one we already talked about, that's the daylight factor. Here you will see always a floor plan of a south-facing office. And near the window, the first row of workstations, in this case, has a daylight factor of larger than 2. So daylit area orange, white, not the daylit area. The next step up from that historically, that was again the observation that just overcast sky conditions are not the relevant sky condition to look at for a lot of climates. So if instead we want to more deal with clear sky, sunny sky conditions, then using the CIE clear sky under equinox or solstice conditions in the morning and in the afternoon might yield us some results. So what you see here, for example, same space as before, but you're seeing for September 21st in the morning and in the afternoon. Lighting levels in yellow, how often are we above about 100 lux? In orange, how often are we above 5,000 lux, which one could say is probably too much. And now the metrics that was used by LEED is combining LEED version 3 for September 21st, 9 a.m. and 3 p.m. and saying what is the area at 9 and at 3 on this day where I have between more than 100 lux but less than 5,000 lux. And this is what you see here. So here the distribution based on clear sky condition is to say wherever it's yellow, we have adequate daylighting. And now enter the next generation of daylight availability metrics, which were climate-based metrics, which really said instead of just concentrating on a handful or less of sky conditions that appear within at a given site, why don't we look at all of them? And for that, really what we want to do, we want to calculate not only a few sky conditions, but any sky condition for every hour of the year that appear at a given site. And there, the main idea to do that was proposed in 1984, even though it took 16 years before it was actually, or 15 years before this was actually fully implemented anywhere. So the idea from Peter Tegenza of daylight coefficients was really that instead of modeling lighting conditions under any particular sky condition, we are creating a scene within a glowing sphere. And then we are keeping track of relationship between lighting levels within a building and contribution to that light from any particular sky patch. And the normalized ratio of this relationship is called the daylight coefficient. And now the nice thing about this, once you calculate these daylight coefficients for each sky patch, then if you want to know under any particular sky condition what the light within the space is here, you're just adding the luminance under a particular sky condition up. You do a linear superposition with a daylight coefficient and you get your results. That allows you to have a pre-simulation process where you do the ray tracing or whatever global illumination method you're using to calculate the daylight coefficients, and then you can very rapidly create sky conditions throughout the year. And there's been a whole series of different climate-based metrics that have been proposed. Just for the interest of time, I'm concentrating on 2 here because they found their way in certain standards over the last couple of years. So one metric is called daylight autonomy. That's mostly used in North America. And what it does, it looks for a particular point within the building, how often I'm meeting a minimum threshold. The definition by the Illumination Engineering Society of North America for required lighting for daylighting is 300 lux. So the question is, how often do I get at a certain point when the building is occupied more than 300 lux? And here the definition for a spatial daylight autonomy is if it's more than half the occupied time, then this called as daylit. Otherwise, it's non-daylit. And so in the left, on the left graph in orange, this again separates the space into daylit and non-daylit area. And useful daylight illuminance added another component to it, which is to say I want at least 100 lux, but I want less than 3,000 lux because 3,000 lux might be too much. Right now, versions of daylight autonomy are used by the LEED Green Building Rating System in the US as a possible compliance path. And my understanding is that UDI, useful daylight illuminance, is used in certain school programs in the UK. So this gives us an idea of how we model daylight within building and how we get a sense of daylight availability over the course of a year in any building on Earth. Now we really want to turn our attention to the second component, visual comfort in buildings. So how are people experiencing a space? And maybe telling as a first step what we've been concentrating on in research first was to define visual comfort as the absence of discomfort, so not experiencing any glare. And to start understanding glare, we can look at the chart that you see here. So this gives you a sense of what the human eye can see. And we have an incredible device to our disposition. We can see luminance levels over 12 orders of magnitude, really. But what's very important, we cannot see ever this whole luminance range at the same time. We can only take in 2 to 3 orders of magnitude. So you can think about whatever level your eye is being adopted here. Anything above or below that level will either appear white outwashed, creating glare, or will be too dark for us to see. So what you can now, when you take this image here, how to design for that, you can say we can take in 3 orders of magnitude at the same time. If we want to read a book in direct sunlight, we already have an issue because we have too large of a range happening in a case like this. So when it comes to daylighting, we somewhat have to make sure that we get enough light, but not too much. So in order to quantify glare in buildings, the holy grail for a long time had been, how do we actually put a number to an image like this? So here you see an image of a workspace. We want to create an algorithm that extracts from the luminance measurement a number which is called a glare index, which tells us a certain likelihood that people are experiencing glare. And there have been a whole range of different glare indices over time, unified glare rating, daylight glare index, and so forth. Really a key innovation step was when we could finally do high dynamic range photography in a reliable way, because that allowed us in a very short period of time to create this luminance maps. And then the first key study was by Jan Wienold and Jan Christophersen, taking HDR photographs in spaces while asking human subjects as well how they felt within the space. And the daylight glare metric coming out of this was called the daylight glare probability. And you see the 2 terms on this page here. Basically, the first term is related to how much eye illuminance do I have, so how bright is the scene overall. And the second term is a contrast term, how much light sources do I have within my field of view. That was a key innovation. Then in terms of daylight simulations, the next step was really that Jan developed a method based on partly daylight coefficients, partly image-based, to predict not only for one point in time, but for the whole year, how much light you have within the field of view. And the outcome from something like this is what you see here. This is a DIVA simulation outcome based on radiance that shows you from January 1st on the x-axis to December 31st for different times of day, if people looking in this direction are going to experience glare. And red effectively tells you there's a problem, yellow is in between, and green is fine. And in this east-facing space that we are dealing with here, we effectively see that in the morning mostly, we are experiencing too much glare, and all the way from the beginning of the year until March, and then starting again in September. And the reason why there's no problem later in the year is, or in the middle of the year during the summer, is because the sun is higher in the sky and doesn't reach the viewpoint that we've been looking at here. So this already allows us to do a pretty comprehensive analysis of glare within the space. The trouble is, once you are switching from an illuminance-based calculation to a glare analysis with a viewpoint, so we are looking not at illuminances anymore, but at luminances, then you suddenly have 3 extra degrees of freedom, because an illuminance sensor just looks up. As a person, we can turn our head, so we can basically 360 degrees look in all kinds of directions. So this is a visualization that was developed by Olsen Jakubiak in our lab, which really looked for different times of day, how much glare would I experience when I look in different directions. So you see here at the bottom for different view directions what the different glare metrics indicate. And so example, in the case of daylight glare probability, when we are looking towards the window, we are experiencing glare because the lighting levels are too high, whereas if we adjust our position slightly the other way, we are fine. And that led then in the same paper to the development of this adaptive zone algorithm, which basically says, well, we should allow people within buildings to move, and our design is better if the furniture and the overall lighting layout allows them to adjust themselves so that they're not experiencing glare. And what you see at the top and the bottom are the same, taken from the same workspace, these annual glare maps, but at the bottom we are allowing the occupants in the space that you just saw to adjust themselves and their computer within a plus minus 45-degree rotational angle. And that reduces glare substantially. Now, another big step that I'm going to show here is this work just coming out of our lab is how do we actually look at glare in a more interactive fashion. So this is a version of Accelerate called Accelerate Real Time. And what it allows you is using either virtual reality or just using a computer screen to zoom throughout a space and get directly glare indication. So on the right-hand side, you see here how much glare somebody is going to feel within a space, depending on which way I look. And the goal for the users is to keep their workspaces green or above, meaning they have enough light, but they're not experiencing glare. And here the big difference is, of course, the moment when you start having occupants doing this in real time, then they can go through a lot more variations in a shorter time frame. And this really shows that our goal, which we had for a long time to make simulations faster, we really have to be incredibly ambitious if we want to use tools not just for optimization or compliance, but for real interactive design. We have to deal with simulation times in the order of seconds rather than hours or minutes. Okay, so now we've covered why do we want to do daylighting, how do we simulate daylighting in spaces, what do we actually simulate, and we got to the point where research is right now. And now there are some emerging topics where there have been a couple of papers as well, and even some first starts in practice to using this method. And my observation is really when you try to look and understand daylighting right now, we have two main trends. We are zooming in or we are zooming out. Meaning that on the one hand side, we are going beyond glare finally. We're looking at light and health in building, and we really try to understand not only when do people feel discomfort and we avoid that, but when is the light actually productive and helpful for them. And on the other hand, we are zooming out, looking at whole urban situations for daylighting. So starting with the first, really the main theory behind this is that for a long time when it comes to daylighting, we've been dealing with the so-called V lambda curve that you see in light gray here, which gives you an indication of for different spectral wavelengths how sensitive the human eye is. So mostly we see, of course, light in the visible range by definition, and mostly green. So all the lux levels, all the photometric quantities that we've been calculating in the past are based on these cones, the color vision in the human eye. And now, relatively recently, we've discovered that there are other so-called ganglion cells within the human eye as well, which have a different action spectrum more within the blue range, and they have an impact on our alertness, on our circadian rhythms, so our wake-sleep cycle. So, and this is very much ongoing fundamental work, but what this for the daylighting research told us is that we really have to get away from just modeling 3 color channels, red, green, and blue, but we want towards having higher resolution spectral simulations. There, a key innovation was done by Melika and Yannicki's lab at the University of Washington, There's a tool presented at IBIPSA 2015 called LARC, which starts off to, instead of using the Radiance 3 color channels, doing calculations for 81 color channels. And what you see here on this image is basically using these simulations to create illuminance levels at the eye, but also photopic lux and circadian lux. So different lux lighting levels based on the different action spectrum for the different cells within our eye. And you see that the results are pretty different. So this will offers a whole new area of research trying to understand how do I basically combine both the visual effects of light on the human body as well as the non-visual effects. This is very exciting. A work that shows where this occupant-centered approach to daylighting goes was just published out of École Polytechnique Fédérale de Lausanne, Marilyn Anderson's lab, where her group looked at 3 different components, such as the health potential, the visual interest, and gaze response driven lighting within zones, and trying to really more zoom in, understanding how occupants are going to feel within a space in a positive way as well. So another innovation that I wanted to cover was, as I said before, the question of how do we apply daylighting by zooming out at the urban level. And that's really important right now because the world population is growing. We passed the 7 billion mark. We have to house all these new urban dwellers in the world. So how are we going to do that? We hopefully we will need to build some new cities, but we also need to densify our cities. So we have to make sure that while we are accommodating more people in our cities, we are not destroying the daylighting for the new city dwellers and the existing ones. So in order to do a simulation such as the one that you see here, which is an urban daylight simulation that tells you that for the neighborhood, you see here 30% of the neighborhood have a daylit autonomy over 50%, so they are daylit. This is the type of information that we want to effectively generate. We cannot do that using our traditional methods because it would take too long, so this simulation took maybe half an hour. So what we're doing instead, we are using a 2-step approach. This is developed by Timur Dogan. When he was in our lab, he's now at Cornell, where we first use a step where we're calculating for every hour of the year the lighting levels falling on the facades of building, and then we are then translating that into a light pulse going into the building. And here's an application where we applied this in Manhattan. This is work by Manos Saratsis, where we looked at the typical Manhattan block and compared total 5 typologies with different floor area ratio densities. And that helped us to identify what kind of typologies are good neighbors and provide ample of daylight for inhabitants in cities. And where we want this to go is basically on the one hand side, we want to influence zoning laws as they exist in New York and elsewhere in the world to make sure that we can densify our cities without losing the daylight that we have within spaces. And then finally, this is work from about 2 years ago, which is daylighting for everybody, so to speak. This is a collaboration with the MIT Changing Faces group. What you see here is a real-time tangible user interface. So this was during a planning meeting of the planning board in Riyadh in Saudi Arabia, where we had this glass table developed by the Media Lab and a real-time annual daylight simulation engine developed by us. And what you see here is people were placing Lego blocks to understand the role of lighting, energy, and walkability within this neighborhood. They would get projected onto the Lego pieces, in this case, daylight availability metrics. And so why this is important is that we help, of course, we change the quality really of the amount of simulations that we can do, and we get buy-in not only from some consultants, but from really populations at large, making sure that we will in future densities still have daylight for our residents. So I'm starting to wrap up. This is a timeline which was suggested by members of the lab yesterday that I should be doing that. This is not an exhaustive historic timeline of innovations in daylight simulations, but it hits the main point that I was talking about today. So the first, in terms of daylight simulations, the first methods available were the Waldron diagrams. Then years later, we had the BRS protector methods. Then Radiance itself was first developed in 1988, even though it's still under development. The first environmental design tool was in 2000, Ecotech. And then we moved on having DASIM as a tool that is widely available for people that want to do annual calculation climate-based methods. Jan Dino's eval glare metric allows you to model daylight glare probability and other indexes in buildings. We have the urban daylight method, and now very recently the large spectral lighting method. So there is a lot of activity going on, and time will show which one of these innovations will take us to a new era of daylighting. Daylighting has been around for a long time. If you look at the relationship between the simulation methods, the physical measurement techniques that we had available at our disposition, and the performance metrics, there has been really a wonderful symbiotic relationship where certain advances in one domain had an influence on the other domains as well. So when we did manage to have daylight coefficients to predict lighting levels throughout the whole year, we had this whole wave of new climate-based metrics emerging. And when we, on the measurement side, when we could finally do high dynamic range photography, we made a lot of advances in the glare field. And this is going to continue, of course, this type of cross-fertilization between different domains. Speed, I want to just emphasize this, really remains an issue. We want to get these simulation tools so that they can really be used interactively in design. And that means that ultimately these tools have to become so fast that they work within the second range, which seems amazing and overly ambitious, but I think we are working towards techniques that allow us to do this type of work. And that will really ensure that daylight simulations become true design tools and not just code compliance tools. So ongoing trends, as I said, are both focusing on occupants themselves, healthy spectral lighting, as well as just generally new modes of practice. With that, I wanted to finish. It's an exciting field. I hope if you haven't tried daylight simulations in the past, then check out some of the tools that are in existence. There's an abundance of tools available. Maybe a few comments on how you should pick a tool. So when you're within a company or in a research group, generally I would say it's very important that you have more than one person trying a tool, but that you create a certain local community, because it's very easy when you're a lone rider using a tool somewhere that you start making certain mistakes and nobody's there to correct you. And then it's of course important to say, well, let's pick a tool that creates the metrics that we're actually interested in. So start with the metrics first that you want to use in practice or in research, then find a validated engine, and that's of course very important, an engine that actually works, that can calculate these metrics. And then finally, you need to pick a graphical user interface that hopefully makes it easy for you and is flexible enough to calculate the metrics that you want. And with that, I thank you, and I'm available for questions.
Thank you very much, Christoph. We have quite a few questions, but I will moderate it and probably will have only 4 or 5 questions.
Okay.
There are quite a few questions. There are quite a few questions on the basics of daylighting, and I suggest the participant to refer to the book, which Christoph was mentioning, or IBIPSA's handbook. And there are 1 or 2 questions on how do some of them reach out to you to study under your guidance. So I would request those people to send an email to Christoph. We will restrict ourselves to the subject matter. We have a question from Eric. And Eric, can I unmute you and you can ask question directly to Christoph? Eric, can you hear me? Yes.
Yes,
go ahead.
I can hear you.
Yeah.
Hello. We are working with glare from PV panels as a part of our master thesis. And therefore we read your article, the Assessing Disability Glare Potential Due to Reflections from New Constructions. And we would like to know how you got, how you translated the output from the photometer into the Ashikman-Shirley materials when you measured the reflectance of the PV panels.
How we did that? How we created the material? modifier for the PV cells? Is that the question?
Yeah, well, we're going to measure PV panels on our own as well.
Mm-hmm. Yeah.
And we would also like to be able to create a Schickman Shirley materials like that.
Yeah. Okay. No, I understand. So just for the overall audience, this is a study that Olsen Jakubiak and I worked on with the Department of Transportation in the US. The background of the story was that there was a very large PV installation at an airport in New England, which led to actual glare when it was installed, that the tower couldn't see one of the runways anymore, which was, of course, a key concern. And this, one should say, is something that will occur more and more often as we fortunately are installing more and more photovoltaic cells. There's a risk of glare of these very large reflective panels. And really the reason why they can create glare quite easily is that rather than being a purely specular reflector like a mirror, they have this forward scattering effect. So instead of having this very thin reflectance of the sun, when you look at a solar cell in the sunlight, you have this white, bright region. And ideally, to measure something like this, you would get a goniophotmeter. Actually, Eric, if you have that. We didn't have that for this project at our disposition, so as described in the paper, what Alston did was he placed the camera at a solar cell into the sun under a certain point in time when we knew exactly where the sun was located, and we just picked a typical angle that the sun would very often have towards the solar cells, and then we took a high dynamic range photograph under this position. And then we tweaked the materials and radiance until the roughness and the specularity had the level that we were expecting it to have. So it's described in the paper. We are happy to give you offline more information on that. This is really all we had in this project, which was incredibly low budget at our disposition. Ideally, if you work with with PV manufacturers, I think it would make a lot of sense to get them to hire one of the labs in the world that has goniophotmeter measurements and that offers to do them for you. I hope that helps.
Yes.
Yeah. Thank you.
Yeah,
we
well,
have a question. Thanks. Yeah, thank you. We have a question from Sneha, and Sneha, I have unmuted you if you wish to ask question directly to Christoph. Hello, Sneha, can you hear us? Okay, let me repeat the question which Sneha wants to ask. The question is that can we use HDR imaging of outdoors, such as sky, to calculate glare indoors and use this information to control blinds?
Okay, yeah. No, great question. So I guess it's a two-part question. First, can you take HDR photographs taken outside and combine them with your daylight simulation to have a more detailed simulation that describes the outside conditions? And the answer is yes. The first person who really showed how nicely that can be done is Milika and Yannicki, who took pictures, HDR, fisheye lens photographs of the sky, and then in a radiant simulation map that image onto the sky. You have to pay particular attention to the sun there, because the sun, you have to add a light source on top of your HDR image to model that correctly. And then the second person who spent a lot of time doing that in detail described it in this very new paper from Nathaniel Jones in Building and Environment, which did a validation. Actually, in that validation, we looked at a series of different scenarios to reproduce an indoor HDR photograph. First, we took a picture just outside of the facade and mapped that in our simulation. Then we took a picture of the outside sky and modeled the surrounding buildings. And then we just used the Paris model. And you can read the various trade-offs there. Now, the question of blind use, I didn't cover that because I was hoping that would be covered in Adeshia's talk, or has been covered in Adeshia's talk. That's, of course, a very exciting ongoing field. How do people actually react then if they feel a certain way, and when do they close the blinds? and we are doing that in our DASIM tool. And you can, if you use that through Diva, for example, you can set a shading system. You can do an annual glare calculation, and that's being used then to open and close the blinds. So, and there are various tutorials available. I'm happy to guide you in the right directions if you want to do this type of analysis.
Hope, Sneha, that answers your question very well. We have a question from Willie Stubber, and she has requested me to read out for her. The question is that, could you see daylight modeling simulation yearly trends being used to control automatic daylight control systems in lieu of photosensors?
Yeah, again, this is something that people have looked about at for a number of years, and no specific study comes to mind, unfortunately, but I know it exists. I think, yeah, there's no reason why you couldn't do that, especially if you see some of these latest tools, such as the Accelerate RT, where you can do real-time measurements. The lag time in that case is greatly reduced, so you could quickly control the blinds. I think the main troubles in the past used to be, where do we get a very detailed 3D model of any building anywhere? This becomes less of an issue, as now in professional practice, Revit models are handed over from the design team to the clients, and the clients are maintaining the model, so that should be possible. Another big question, I remember, I think Adeshi Madabi worked on that, for example, was, well, when you have any furniture within a space, how do we make sure that when occupants change position or furniture changes, that the simulation is still going to work? These are real-world problems, but in principle, nothing prevents you from overcoming them over time.
Okay, thanks. We have two more questions. Probably I will take. One is from Livia Martins. She wants to ask, in multi-directional simulation with Radiance shown, it's possible to know if glare came from surroundings and percentage of it?
I guess the question is here, how do you identify when you take this high dynamic range photograph images and you are detecting glare, of where the glare is coming from? I think a good workflow there is that we've done that in the past, is that when you design, for example, a classroom, you pick certain positions of where the student and where the teacher are typically facing and looking, and then you do these annual glare maps that I showed earlier for the whole year. So that gives you very specifically the times in the year when there is a problem. And then ideally you run an actual luminance simulation of that scene, and then you see what the glare issue is. So in the case of eval glare, it gives you in color what it interprets to be the glare source. And then you, by just looking at the image, you see, is that a reflectance of my desk, or is it sunlight in the field of view, for example?
Okay, thank you. Ian, can you hear us, and would you like to ask a question directly to the Christoph? Ian Van?
Oh, hi there.
Yes.
Hi, Christoph. I was just looking to ask if you had any advice for achieving LEED v4 compliance in areas with low sun angles, so lots of glare occurring.
That's a good question. I mean, if you followed what I wrote about that, I can share that with you. In Lighting Research and Technology, I had a Reason and Opinion where about the LEED v4 metric. So I'm of course thrilled and happy that spatial daylight autonomy is a metric there to evaluate the amount of lights that you have within buildings. At the same time, there's a relatively new metric that still needs, in my opinion, further validation, is this annual sun exposure, which is used to drive the blinds. So when you have more than, I think it's 1,000 lux at more than a certain percentages of points within your buildings, then LEED v4 wants you to close the blinds. And as you are probably aware, when you try to design in certain climates with this situation, then your blinds will be closed most of the time, and it's very hard actually to get the required v4 levels. I think one way, this is more really I would have to defer if lead accepts that. If you say instead of using the automated blind control that lead v4 prescribes, but instead you measure your own automated blind system, you simulate your own automated blind system, and you say we will have basically sensor-controlled blinds in space that we open and close. That might give you more leeway to not having to close the blinds as often. But I think that this is really a work in progress. I think we have to fine-tune, especially for this low sun altitude angles, the way we are prescribing when the blind should be closed and opened.
Okay, thank you. And probably we'll take a last question. We are really running out of time. Raul Ajmat, can you ask question to Christoph directly? Raul, I have unmuted you. Okay, I don't think that he can. Okay, let me ask a question on his behalf. Raul is asking that which would you think is the best way to predict annual irradiation values in urban environment in order to evaluate photovoltaic feasibility?
Oh, photovoltaic feasibility. Well, there's some work that we've done in our lab to do this. You can effectively model whole cities and then just model the PV potential in buildings for rooftops. So typically what we actually do in our first year class here, that the architecture students first start doing using radiation maps. So this is something that is available within NIVA, for example. That's a radiance-based way of getting a false color image of an urban environment that tells you how much light falls on every point within a building over the course of a year. And that helps you to understand where the areas within a city that provide you with sufficient photovoltaic potential, so to speak. And then you can add on top of that, for example, an Energy Plus model that then fine-tunes the results and gives you an exact result, how much the PV potential is. I mean, there's a lot of work on this that we've done, and if you don't find them online, I'm happy to share them as well.
Thank you, Christoph. I think we are running out of time. You have another lecture to attend in your institute, and I'm sure that we need to. Yeah. Yeah. So I request people to send an email to Christoph as and when they have a question. Whenever he has time, he will get back to you with the answer. Christoph, thank you very much, and I'm glad that despite all the last minute rushing around, you could offer wonderful webinar to us. Thank you from EBIPSA. Thank you very much.
Thank you, Rajan. Thank you for having me, and yeah, please ask any questions. Thank you for giving me this opportunity, and bye-bye.
Thank you. Bye.